All right, hey guys, and welcome back to another AP Physics C video. Today we're going to be doing the electric field from a infinite line of charge. You can see that by these two little squigglies. This means College Board will use these two little squigglies to show that this stretches in this direction infinitely, and this stretches in this direction infinitely. They just don't want to draw it. That's just common notation. But yeah, like I was saying, we're going to derive the electric field at a point that is at a perpendicular bisector of a line of charge that stretches infinitely to the positive x and the negative x. So let's just jump right into it. What your initial intuition might think is if we take out little dq's of this infinite line of charge and we use this equation, E equals k dq integral dq over r squared r hat, and our bounds would be from negative infinity to infinity because that would be the length. Then we can find an electric field. Now you could do that. That's definitely an option. It's just AP Physics C won't actually ask you to do that because there's a much smoother and much more comprehensive way to get there without using improper integrals or using a trig substitution because that method would require a trig substitution. And today, I'm going to show you guys how to do this without trig sub using something called Gauss's Law through Calculus 3. Now, AP Physics C doesn't test you on the Calculus 3 necessarily, but they do test you on the conceptual understanding. So that's what I'm going to give you today. So let's look at this. Let's imagine this little cylinder. This is a pink cylinder, right? So what I want you guys to imagine is, let's say we take this imaginary pink cylinder called a Gaussian surface, and I make it coaxial. That was bad. And I make it coaxial with my line of charge, right? So when I say coaxial, I want to use this water bottle analogy. So I have this water bottle in front of me. It's kind of like a cylinder. I'm going to treat it like a cylinder. If I place a pencil inside of that water bottle, that will look something like this, right? If I place a pencil there, that'll look something like this. Now, if you have a water bottle and a pencil, go ahead and do this. But you can see that if I put the pencil smack dab in the middle of the water bottle, those two are coaxial. The pencil in itself is kind of like a cylinder. I could treat it as a line. And if I imagine that pencil has charge, let's think. The electric field, right, is proportional to 1 over, sorry, that says equal, is proportional to 1 over r squared. So you can imagine the electric field of this pencil with charge radiate, or like kind of radiating outward, right? It goes in a radial direction out from the pencil because it has positive charge density, right? But if I pick a radius, right, because at the center of the pencil, that's radius equals 0. If I start moving radially outward from the pencil, what would the electric field be there? And would the electric field be the same for all of these points? Let's call this r equals c, right? Because in this instance, if you imagine this, this is basically the same cylinder. Those two are the same situation. And this is the radius because this is y equals 0, and that's y equals c. Our radius is c. You guys can visualize that. But as I was saying, let's say we pick the point r equals c. Will the electric field be the same for all of those radiuses r equals c? And the answer is yes, because the distance from the line of charge is the same for all of those. It's equidistant from the center, from the line of charge. So therefore, the electric field must be the same for a radial distance that is the same. So now that we've gotten that over with, now let's think about the Gauss's law portion of this. So I'll probably bring this diagram back later, but Gauss's law tells us that the electric flux through a surface is equal to the enclosed charge divided by epsilon naught. Now, epsilon naught is this constant, 8.85 times 10 to the negative 12, and I forget the units, but you really don't need to care about the units. It's Coulomb squared per Newton meter squared. It's a constant. It's kind of like Coulomb's law constant. I'm not going to say more about it besides that, but it's in Gauss's law, and this is Gauss's law. Electric flux is equal to Q enclosed divided by epsilon naught. Now, let's think. What else is electric flux, right? Electric flux is also electric field at a specific point, dot A. Now, if we had a two-dimensional surface, this would make sense, right? Just a regular flat square, or maybe even a parallelogram that has a tangible area. Let's say the electric field passes through it, right? And it has the same theta for all points at which it passes through. But when we go back to that water bottle, right? Now let's think, well, what's the electric flux doing here? how at each little point, because the surface area, right? Or well, the surface, right? Our surface, what is our A that we want to measure the electric flux through? Well, what we want to is if you have that water bottle still, we want to measure through the surface of the water bottle. Now I want you to think, if the electric field, I'm going to draw the electric field in pink, radiates radially outward, right? Kind of perpendicular to the surface of that pencil, what else will go radially outward from a surface? And if you said the area vector of the water bottle, right? You're right. Because at all points, I'm going to think about all points as dA. So a little small chunk, I'm going to actually do this in red over here. I'm going to pull out right here. Here is dA. Now dA is a small, I'm going to actually do this. Or that's dA, not that. So that is dA. A little small patch of area within the water bottle that's infinitely small. So if I imagine at these little patches all over the water bottle, will the electric field vector match up with them? And the answer is yes, because by definition, the area vector of a surface is perpendicular to that surface. But since the pencil and the water bottle, right, are coaxial, we know that electric field is also going to be perpendicular to the surface, like of the line, right, or the cylinder, because you can have a cylinder of charge that has linear charge density. That's what AP Physics C does. But back to what I was saying, because the electric field radiates outward, it's perpendicular kind of to your pencil surface, and the area vector is perpendicular to the water bottle surface. So guess what? The theta between these two, when I do the dot product, I'll transform this now. When I do the dot product, E dot dA, for every single dA and for every single E, right? For every single electric field that corresponds to the dA, cos theta will be 0 because they both radiate outwards and they both point in the same direction. Therefore, the theta between the two, right, isn't like this. It's not like this. No, it's actually like this because they point in the same direction. So now I have this equation, right? This is the electric flux, E dA cos 0, and cos 0 is just 1, so I'll cut that out because we don't need a multiplier of 1. We know 1 times anything is itself. So now I have the electric flux for little patches is E dA, right, of this specific situation. Now, all of these little patches, right, if I sum them up, that makes the whole surface area of the water bottle. So now how will I do that? This is where calculus 3 comes in. In calculus 3, if we put this little thing called the line integral, that will sum up all of those little patches and make it so that we look at the whole surface of the water bottle. So now this, if I put the line integral over here, this is Gauss's law. This. So I'll pull this diagram if you need it somewhere else. And I'll write the formal version of Gauss's law. So what people really want to say with Gauss's law is that the enclosed charge over epsilon naught is equal to the line integral of E dot dA. And if you don't know what a line integral is, that's fine. You just need to know that when I take the line integral of dA, that gives me surface area. That's all you need for Physics C. That's all you need for now. When you take Calculus 3, if you take Calculus 3, you will know. But besides that, you don't need a conceptual understanding that deep. And if you would like one, I would recommend that you go look on YouTube or even ask ChatGPT. That's how I learned it. Right, let's continue. As I was saying, so this is the formal definition of Gauss's law, right? But on the right, if I compute that vector dot product, I get E dA cos 0, like I was saying, for this specific situation, and only for this specific situation, right? Because of the symmetry. This is what Physics C would normally give you, the symmetry of this Gaussian cylinder. That's why we picked the cylinder in the first place. We didn't pick a cube to be our Gaussian surface, our imaginary surface that we're going to measure imaginary flux through. We picked the cylinder because it allows us to use Gauss's law with symmetry and not have to do all of this complicated calculus. So cos 0, right? This goes to 1, and now I get line integral E dA. But as I said, for that water bottle at a radial distance that is R equals C, the electric field will be the same because it's equidistant from the line of charge. So I can just pull out my constant from the integral and I get E dA. And like I said, the line integral of dA, right? That's some people call it a surface integral, is surface area, and that's just an abbreviation, surface area. So now we need to think. This is a little bit more complicated because some of you might intuitively think, and I thought this myself too. So if you're thinking like this is the right path. The surface area of this surface, right? Well, if I want to measure the electric field at y equals c at the radial distance r equals c, then shouldn't my radius be, well, c? And you would be right. So the the surface area would be 2 pi r, but r would be c, and times L. That's why I had this L over here in the first place. Sorry, I didn't mention this, but when we define the surface area, this Gaussian cylinder, I drew it that it's kind of closed, but since this extends to infinity, right, the Gaussian cylinder will also extend to infinity. But in physics C, you might be, oh, sorry, in this situation, you might be thinking, well, what about these ends? What about this? Don't you have to add 2 pi r squared, right? In order to, no, in this situation, you don't. Because in physics C, it is very common that you ignore edge effects. You might be saying, well, that's not right. Isn't the flux different, right? If you ignore the edge effects? Technically, it is not. Because if I look at the edge, this will produce an electric field this way and an electric field this way, and they will just cancel. The fluxes through them will just cancel because they're not producing an electric field. Sorry, they're not producing an electric field in the y direction like we want. We don't want x direction. And one flux, actually, sorry, the fluxes won't cancel, right? They'll have the area vector is this way. The fluxes will be in an x direction that we don't care about. We care about the y direction, so we're not going to include this because in the course exam description for AP Physics C, even you can say that they often ignore edge effects. And edge effects is what I just said. Like don't think about plus 2 pi r squared. Just think about the surface area as being 2 pi CL, right? So knowing that we're going to ignore edge effects, now our surface area, we can sub that in here, E 2 pi CL. And now I'll bring down that left side where Q enclosed divided by epsilon naught. So now I have this equation, Q enclosed divided by epsilon naught is equal to E times 2 pi CL. And you might be thinking at this point, well, E times 2 pi CL, wouldn't that just be infinity because L goes to infinity, the length is to infinity? I'm leaving L like that on purpose because I know it will cancel later, right? So ignore that for now and we'll keep going. You'll see how it plays out. So now I want to think, well, I'm not allowed to leave Q enclosed in my final derivation because that's not one of the given terms that they gave me. They gave me charge density and they gave me length. And fundamental constants as appropriate, right? That's just normal. And they also gave me C. So now let's think, how can I get to the enclosed charge from lambda? Well, they said uniform charge density. So I know lambda has to be Q over L. But I know since I'm enclosing this entire line of charge, sorry, this is the wrong L, Q over L. I know since I'm enclosing the entire charge, right? Since I know that I'm enclosing the entire charge, my enclosed charge will be this big Q. So Q enclosed divided by L equals lambda. That was big word, whatever. I don't know what I just said. Hopefully that made sense. If you have questions, please put them in the comments. That's on me. But yeah, so like I said, Q enclosed divided by L is equal to lambda. So if I just do some arithmetic, lambda times L is equal to Q enclosed. And hopefully that makes sense because lambda is really a ratio of charge per length. So if I multiply by the whole length, then I should get my charge, which I did. So now I'm going to say lambda times L, right, subbing in for that Q enclosed, divided by epsilon naught equals E 2 pi CL. Now guess what? L is on both sides, so I will cancel. And now I get lambda divided by epsilon naught is equal to 2 pi C times E. So I'll just divide by 2 pi C on both sides, right? And then I get my final derivation that the magnitude of the electric field is equal to lambda divided by 2 pi C epsilon naught. And there's the final derived equation for this Gauss's law problem. Hopefully that made some more sense and the patches of dA made sense because that is the most difficult conceptual thing. So just to recap, whenever you're doing a Gauss's law type of problem, whenever you're asked for something Gauss's law related, you're going to have to use a Gaussian surface. The way you pick these Gaussian surfaces, usually for physics C, it's one of two things: a cylinder or a sphere. When you have a point charge, something spherical that appears to have spherical symmetry, right? You pick a sphere as your Gaussian surface. For example, if I had a point charge, right, and it radiates outward, kind of making a circle, right? I can visualize a Gaussian surface that is at a radius, I guess you could say r away, in order to measure the electric field. And the Gaussian surface would be a sphere, and the only thing you would change is when you would do the same process like this up until this point the same, right? You would take out, what's it called? You would say that the cos between all E's and all dA's is 0, because that's how AP Physics C will always have it. Usually there will be symmetry, right? It's very uncommon for them to not have symmetry. They can't test you on something without symmetry, because that would require actual calculus 3. They might ask a conceptual question like, what if this didn't have symmetry? How would that affect the flux? But you'll see that when you see it. If you have a question like that, please put it in the comments. I'd be more than happy to answer it. But as I was saying, you'll do the same process. You'll say cosine for the cosine between every dA and every E at those dA's is 0. Set that to 1. You'll pull out the constant E from your line integral. You'll say line integral dA is the surface area. The only thing that would change is the surface area of the Gaussian the Gaussian surface. Now it would be a sphere, so it's 4 pi r squared instead of 2 pi CL. And that's it. It's the same process, the same derivation otherwise. So hopefully that helped. And I'd love to answer more questions in the comments. Oh yeah, wait, I forgot to say one last thing. When you have a line, a wire, or a cylinder, pick a Gaussian cylinder. When you have a sphere or a point charge, pick a Gaussian sphere. But yeah, that's pretty much it. I hope you guys enjoyed this video and it made some more sense. And yeah, I'll catch you guys in the next one.